Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Last class we were dealing with the heart of oblique shocks, primarily how to look at oblique shocks and what is the connection between the deflection angle and the shock angle for a given Mach number, etc. Today we will go into one aspect which we did not finish, but before that I just want to recap a little bit. We drew these pictures for any given beta, and we found that we can make the same theta happen for different beta values. The way we drew it, if I continue the same procedure, I can draw for 10 more beta values, but only 2 of those, actually there is only specific 2 of those will match with the u2 normal divided by u1 normal from normal shock tables. Okay. So, all the other things we can follow the procedure and get more of them, but only 2 of them are exact correct solutions, of which the one with higher beta is the strong solution, one with lower beta is the weak solution. Okay. And we looked at in a weak solution it is changing kinetic energy very little, in the strong solution it is changing most of the kinetic energy into internal energy. Those were the details we saw, and then finally we said that we can use P02 by P01 from normal shock tables as such to get P02 by P01 for oblique shocks, but I would advise you not to use that because it will cause a lot of confusion. Okay. That is all. It is safer to go by just finding Mach number and P2, and from there M2 and P2 you can find P02 from isentropic tables. That is a safer way to find P02. Otherwise, if you happen to have this other column which I have in my gas tables, P02 by P1, that will not give you the correct value. Okay. So, just to avoid confusion, we will just follow a single procedure which will always be safe, which is we will not use P02 by P01 from normal shock tables to obtain P02 by P01 for oblique shocks, can be used for normal shocks. Okay. Now, we will continue along the lines of yesterday, and we will go back to the original picture. This is our shock angle. There was a 90 degree and 0 here. This is your deflection angle theta, and there is no limit for this. I will just draw a particular case. I drew slightly over beyond this. This is a little better than that. Something like this, and we said that for any given theta there will be 2 solutions, the weak solution and the strong solution, and we found that this was mu for that particular Mach number for which you have drawn the line, and this is 90 degree which corresponds to normal shock solution. Now, we have to look at, there is a particular theta above which there is no solution for oblique shocks, there is no solution for a beta value above this. Okay. That means there is something special happening above this point. What will happen? So, you will go draw that picture of oblique shock happening. If I consider this is my theta, typically we will have a shock like this with an angle beta, okay, and the flow vector will come like this, will turn and go parallel to this wall. I am saying it is a wall, it need not be a wall, it could be a stream tube, it could be anything, just all I care about is the streamline turning like this. Wall is very easy to work with, so we will just remember it as a wall, it is easier to tell. Okay. Now, I am deflecting and it is a sudden corner, okay, it is a sudden corner, people call it sudden change in angle, its slope is discontinuous there. Okay. And this is what I will have, and I have drawn it such that this vector is very long, this vector is short, okay, it is consistent with theory, okay, and this is for some particular m. Now, if I for this particular m curve, if I go look at the theta beta for a particular Mach number, I will find that it has a theta critical, theta maximum. What if I keep on increasing this theta? I will draw one more. let us say the deflection angle for the wall is theta greater than theta max. If such a thing happens, then the shock will not be along this line starting from this corner, but it will be detached from this corner and it will sit like this. Okay. It will be close to a normal shock at the bottom, and as it goes out it will turn out like a bow shock. We saw an example of a bow shock in one of the videos some 2 classes back. Okay. So, it will look something like that. Okay. Now, the flow here is going to come straight, it is going to see that it is almost a normal shock, actually very close to the wall, it is a normal shock. So, the flow will just go straight and the flow here will be subsonic. As we know from normal shock, the flow downstream is subsonic, and somewhere here, if I pick this point, it is an oblique shock locally with that particular beta value, and here there will be a deflection like this. When I go far away, if I go up to very long distances out, I may go to a point where this angle is very close to Mach angle for that particular Mach number, that is, it is a very weak wave finally. It starts as a very strong wave for the given Mach number, this is the strongest possible compression wave, that is your normal shock. As it goes out, it is getting weaker and weaker, and it goes to a point where P2 by P1 equal to 1 at very far distances from this change. Yeah, I am telling you again, from this change only everything matters. Very close to this change, there is a normal shock. Far away from the change, its effect is lesser. P2 by P1 effect will be lesser. This is a simple way of looking at it. If I look at it from a point of view of there is a wedge shaped body in flow, I am considering 2D flow. If I have some particular semi angle less than theta max, then I will have an attached shock like this. This is my body and there will be attached shock like this. The streamline that is coming here will turn around and go like this. Here the streamline will come here and go like this. Okay. This is just a mirror image problem, so I will not worry too much about this turn. It's, you can convert it to be a minus theta and a minus beta, it will work fine. Okay. So, that is this case. If I have theta greater than theta max here and I have a problem like this, flow incoming is having a Mach number m and it is uniform, and what we will see will be a bow shock, similar to what we saw over in front of a sphere in the video 2 weeks back, 2 classes back. Okay. It will look something like this. Okay. And there is a particular detachment distance. This detachment distance depends on the gamma value, depends on how long is this straight line, is it going forever. If it is going forever, it will be a particular value. If it is stopping somewhere after some distance, like in a missile or something, if it becomes straight after some time, then this will be a little closer, and it is related to where the shoulder is, shoulder of this wedge. Okay. We will not worry too much about it, that is not related to our problem. Now, I want to look at, let us say this particular case I will pick. What is happening in here when I go to some case here? Last class we said that strong shocks do not occur in steady problems. Okay. That is only for attached shocks. Okay. Now, I will qualify that statement again now. Okay. Last class we said we have strong shock solution and weak shock solution. Strong shock solution is proven to be unstable and it will not occur in a steady problem. That assumed that I am going to have a deflection like this, where it is a attached oblique shock. If it is a bow shock, it so happens that I am having a normal shock here, and as I go up, it is going to go to from 90 degree beta angle to something less than 90, slightly less than 90, so it is going to go from 90 to 85, 80, 70, 75, 60, whatever, all the numbers will be there, and far away, if I extend this very far away, somewhere far out, it will become Mach angle for this particular Mach number. Okay. Which means if I go back to that curve again, for my bow shock, at the center line it is here, and it is sweeping through the whole curve for that particular Mach number. Okay. It is having all the compression waves possible in this curve. It is going to have all solutions in this. Okay. That is one observation we want to make. Okay. Now, the one more thing I will just tell from here is, if I look at it, it starts with M1 normal very high, and it goes all the way to M1 normal 1. Okay. M1 normal will become 1, that is, it is not going to have any P2 by P1. Okay. It is going to go through this whole sequence, M1 normal very high to M1 normal nothing, M1 normal equal to M it will start with, that is 90 degrees, right, sin beta will become 1, and I am going to end with sin beta equal to 1. Okay. So, I will end up with sin beta will become 1 by M1, so it will become 1, M1 normal will become 1 here. Okay. We will end with that. Okay. If I look at M2, the Mach number behind the shock, it starts with subsonic, it is going to go, we already had this dotted line we drew last time, it was going like this, we said this is M2 equal to 1 line, and we said this is our theta max line, we had two curves like this going across different Mach number lines. So, if I think about it, it starts with very low subsonic, this is the strongest shock, very low subsonic, and is going slightly higher and higher Mach number, and then up to here it is becoming m equal to 1 at this point, that particular beta value it will be m equal to 1. After that it is decreasing, it is further increasing to supersonic values up to a point where it becomes finally m2 equal to m1, goes all the way to there. Okay, that is, it is a Mach wave where there is no change, so m2 equal to m1 becomes that, it goes from the whole spectrum. Okay. The next thing I want to look at, theta value, this is more difficult. Theta value is 0 initially near the center, as it goes up it is increasing, goes up to the maximum value possible for that Mach number, theta max, and then it drops again and goes to 0 again. Now, I want to draw this picture, actually I will have this picture, I will erase the top picture, I do not want to draw this so much. Okay. So, I have this picture where I am having theta greater than theta max, so I am having a detached shock sitting here, and let us say it is going all the way up to oblique Mach wave somewhere here, let us say this is my Mach wave line. If this is my mu, then the streamline that is coming here does not change, it just goes straight, that is far away from the change. Okay. And very close to the change, we said it is 90 degrees beta, so it is going to be just going straight, normal shock. Somewhere here it has a small theta, so it will turn a little bit. Let us say this is my beta corresponding to theta max, this particular thing, let us call it, I will just put this arrow and call it theta max. Okay. The deflection at that particular line, I do not know where it is somewhere, that particular line will be theta max. After that, now I am going to have again decreasing streamline angles. Okay. That fine, I will leave that one, we will draw the next one with lesser angle. Something like this. Ideally I am supposed to draw these vector lengths also correct. We know that this will be the lowest, and as it goes up the velocity increases. So, vector length should be increasing from here all the way up to there, where it becomes same length as that, all the way together. Now, if I look at this area, this one line has the highest theta, on both sides it has lower theta, which means this one will want to go crash into this streamline, that is, there is extra compression happening after the shock. Okay. There is something more happening after the shock here. Okay. Such things are also possible. In most cases, somewhere up to here will be subsonic flow inside this region. Okay. Why am I saying that the theta max will be in subsonic range? We go back to the curve. Theta max is sitting in a point where m2 is subsonic. Okay. That is all I am saying, and slightly below theta max on the beta lower side is where you will have m2 equal to 1 happening. The only point where m2 equal to 1 touches the theta max is at m equal to infinity, we will not go there, okay. And of course m equal to 0 also, when there is no flow, no shock, we will not worry about it, okay. So I am having this whole region inside here, inside this curve all the way inside this whole range is all subsonic flow, okay. All this time when I had this nice attached shock condition, the flow could adjust to this change, that is change in streamline direction, by just having one attached shock, that was enough, okay. Just change in angle of the flow direction, and that was enough, just having one oblique shock. If I had the change too strong, then it has to change very fast, which is not possible for a fluid. So what it does is, it makes the flow go to subsonic, has a velocity very slow, temperature very high, so speed of sound is very high, velocity is very low, so it will have very nice feedback in here to adjust to the situation, okay. What happens is, after this the flow has become subsonic, and then now the subsonic flow knows where the fluid is. If I think about steady state, where the wall is, if I am thinking about steady state problem, we are considering only steady state problem, final state, we will deal with a shock forming in front of a oblique shock, in front of a wedge towards the end of this course, currently no, okay. And what will happen is this, if I just look at this region of the flow after the shock, it looks as if there is a subsonic flow over a wedge. What should it do? It will just start turning like this and go very slowly, it will start turning. It is subsonic flow anyway, it can find its own way to adjust, it will do something like this and adjust. It will have region of contracting stream tubes. What does that mean? Subsonic and stream tube contracting, area decreasing, subsonic Mach number will increase, okay. That is also happening in here. So we are accelerating the flow here, okay. That is why this dotted line, which is corresponding to sonic line, we call it the sonic line, which is nothing but m equal to 1 there along that line. I will go to a point where m equal to 1 sits here, okay, and after that the flow is supersonic, okay. It so happens that typically I will have to modify this picture such that the m equal to 2 line, m equal to 1 line will end on the shoulder of this body, typically that is where it stops, okay. If it is the other way, it will find it unstable, okay. This is the only place where it will find it easy to adjust, okay. So it will typically be sitting here if it is a wedge problem, okay, something like this, okay. So we have to think about what is happening inside here. Of course I already gave you the answer, stream tubes are coming closer and closer after the shock, it becomes subsonic and it is coming closer and closer, which means it is going to accelerate again, go to supersonic condition. Once it goes supersonic here, there is something more that will happen here which we have not explained, we will come back to that. The flow has to turn back here along the wall, we will come back to that later, okay. Next class onwards we will deal with that, okay. So when I go here, this streamline is going to accelerate to go there. There is something more which I have to talk about, let us say towards the last 1/3 of the class, a course where I will talk about this region having a lot of vorticity in it, hey, it is not a simple flow. All this time we ignored any rotational flow, we said our flow is completely irrotational, we do not need to worry about any of those del cross terms, actually we just said mu equal to 0, even if there was del cross terms we would not worry about it, that was what we said, okay. Now we will just say that this flow is very rotational behind this bow shock, okay, and we will just leave it there, we will not do anything more about that. And I said that depending on how far this shoulder is from the starting point, the curve will shift, okay. If I had a case, I will draw there, no. Let us say I will draw only one side, I will not worry about the other side. If I had a case like this, then let us say my bow shock is like this and my m2 equal to 1 line is here. If I had another case where it goes beyond and then turns. If I had this case, it will most likely be looking like this. There will be a higher standoff distance and this whole region will be filled with subsonic flow inside here. Of course, the flow becomes supersonic after some time, even for this streamline. The streamline that comes here will turn, accelerate to supersonic. At this point it becomes sonic and then it is supersonic, it does that. Okay. We won't worry about that for the moment, we will just leave it like this. Okay. And one more thing I just want to point out, the streamline that is going here is processed by a different shock compared to the streamline that is going here compared to the streamline that is going here, which means each of them will have different entropy jumps across. Of course, we can easily say that M1 normal, the normal Mach number is the highest, it is equal to M1 here, and as it goes up it is M1 normal equal to 1, it becomes as it goes out far, which means the strength of the shock or the delta S, the increase in entropy will be highest here. As it goes up, the entropy increase is lesser and lesser and lesser. Okay, one more observation, we will not do much with it currently, we will come back to it after some time. Okay. Now, I just wanted to tell you something extra so that you will have a little more physical feel for this. Okay. Of course, I cannot give you very good physical feel because it involves math after some time. So, anyways, we will try it a little bit. Okay. I wanted to give you a slight feel for why will there be two solutions. Okay. If I keep on increasing my beta value from say Mach angle to very high angles, the theta will keep on increasing up to some time and then it will start decreasing again. We want to see why. Okay. That is the goal. It is easier done if I go to my fixed normal shock, which is vertical, and an observer is moving with velocity v here, the very first thing we did with oblique shock class. Okay. We will start with this and we will say that I am going to have a particular incoming Mach number M1 irrespective of what beta I have for the shock, which means my V1 value is a fixed value. V1 is fixed, it is V1 by A1 is my Mach number M1, okay, and I am saying incoming gas is having a particular speed of sound A1, we are starting with that. Let us say we are considering the vector that is going through that point. I will take this as the length of my vector V1, okay, and if I want to change the beta, it is going to be beta is what? Beta is nothing but this angle, right, the angle the shock makes with respect to the incoming streamline, that was beta, right. In here we said this angle is beta, okay, that was our beta locally. The shock makes this angle with respect to the incoming streamline. So, here this is my incoming streamline, shock is making this angle. So, I am having very low beta value. Of course, I cannot have very low beta value close to 0, minimum possible is mu, we proved it last class, okay. Below that it will go entropy less than 0, okay. So, there is a minimum possible, let us say this is our close to minimum possible, it is slightly more than mu, we will keep it like this. The other possibilities will be the vector can be here. Oh, I have to draw the vector other way. Okay. This can be my vector and I have to make sure that the lengths are the same. So, I will draw a circle along this with that as center. So, it has to be this length, it is not a good circle, but it is reasonable, okay, something like this, and I can have close to normal, that will be a shock like this, so that will be a streamline like this with respect to the shock, something like this. We want to see what happens in these three cases. Let us pick this particular case, the lowest beta value. What I have to do is just go and draw the normal component and the tangential component. For this small beta value thing, you find that the u1 normal is very small. This is my u1 normal for that case. if this is the u1 normal, the change will not be very high because the m1 normal is exactly the same for all the cases. Okay. The change is not going to be very high, okay. Or even if there is a change, the velocity vector, say I multiply by 0.5, then I am going to say this vector is going to become only this length, the normal velocity vector. Tangential is still going to be the exact same length. Okay. So, I will erase this v because it is confusing. I have to draw roughly the same length. Okay. Let us say this is my u2 normal. I just guessed a value, something that is smaller than this u1 normal. So, now my final velocity vector, I am curving, I will come from there. This will be my final velocity vector. If you look at it, there is a very small change, but it is not very perceptible. Okay. There is a small change. If I extend it, it has changed by this much. This vector, if I extend it, it will go along this line and it has changed by a little bit. Okay. That is a small theta value. Let us go to the other extreme, this highest beta currently we are considering. Here normal component is very high, this whole thing is normal component, and this is my tangential component. Okay. In this case, for this shock the incoming velocity is very high, which means it will drop very high. Okay. It is a very high incoming flow, it is going to drop very high. Unless I use the normal shock tables, I cannot exactly tell what the value will be, I am going to guess again. I will pick the tangential value to be somewhere here, it should be the same length here, and then the normal, let us say I will put somewhere here, I do not know where it should be, I will consider this to be my u2 normal for this case. Okay. So, I will end with this, and that value is somewhere here. Now, again I have to find the deflection in the streamline. So, I have to extend the original streamline. This is my theta for this case. Okay. The way I have drawn it, it looks like this is slightly bigger than this. Now, we will go to the next case. The next case is something in between, and I am assuming this is going to be close to your theta max somewhere, I do not know where exactly. So, I will draw the normal and the tangential on this. Now, this is somewhere here, this length same tangential, that will be here, this line. Now, I have to look at the shock strength, it is going to be some u2 by u1 in between this case and this case. Okay. Here the u2 by u1 we said was roughly half, in the other case it looks like it is that full amount is covered in 1, 2, 3, 4, 1/4. So, let us pick 1/3 for this case, u2 by u1 is 1/3, let us say in this case. Okay. If I pick that, then it is going to be that distance somewhere here. I am having so many confusing plots here, but that is the only way I can explain this. I missed it slightly, it is okay, we will just take it like this. It is going to be this particular case. I will number it 1, 1, we said this was our 2, 2, this is our 3, now this is our 3. What we are finding here is this one extends somewhere here, this is my theta here. What we are seeing is when I have 1 I have a low theta, when I have 2 I have somewhat less theta compared to 3. Okay. I am going from lowest angle possible for beta to 90 degrees. As I go, what we are finding is theta is increasing and decreasing. Okay. Am I giving you complete physical feel? Not exactly. Okay. So, I will give you a better example by just going to math, a little bit of math. I want to find this angle theta. How will I find it? It is just tan inverse of this vector components divided by minus the tan inverse of this vector components, right. So, I will just write it directly, tan inverse of V by u2 normal minus tan inverse of same V divided by u1 normal. Okay. This is the formula we are having for that, right. It is a simple enough formula. Of course, we know that the V is the same, but V depends on beta. Okay. How does V depend on beta? V is equal to V1 cos beta. We can of course find it out, it is not that difficult, we wrote it for Mach number before. Now, I will write u1 normal is V1 sin beta. This is how you got m1 normal equal to m1 sin beta from here. Anyways, so if I say my beta increases, if my beta increases and beta is somewhere between 0 and 90 degrees, if beta increases, cos beta decreases. We said fixed V1, right. So, V decreases. Okay. Here V1 is fixed, 0 to 90 degrees, sine will keep on increasing. So, if beta increases, u1 normal increases. Now, I will go look at this term, okay. V by u1, V by u1 normal. If my beta increases, V by u1 normal will decrease, because denominator is increasing, numerator is decreasing, simple enough. Okay. And tan inverse is a monotonic function. I have to draw that also here, I will draw it here. This is some x and this is tan inverse x. This function is going to look something like this, it is close to 45, I think it is 45 at the 0 point, and it is going to go like this. This is the function for tan inverse of x, where x is your angle, x is your number and this is your angle, yeah, right. Okay. So, x can go anywhere from 0 to infinity. So, what we are seeing is if beta increases, this quantity decreases, which means I am going this way on this line, what we will find is tan inverse of that quantity will decrease, which means I have a tendency for increase in theta based on this. If I increase beta, my theta will increase, that is one aspect. Okay. Now, we will go to the other one. V is still the same, V1 cos beta, good enough, we will keep it that way. Okay. I can also say it is V2 cos, let us not worry about it, V2 cos beta minus theta, it is not complex. Okay. I will write it now, u2, what happens to u2 normal if u1 normal increases, okay, that is the idea. u2 normal is actually we have a function for u2 by u1, we will just keep it like this, u2 normal by u1 normal is equal to gamma minus 1 m1 normal square plus 2 divided by, actually I am getting too cluttered here, I will write it all in the next place, next board. u2 normal by u1 normal equal to, this is same as normal shock formula, m1 normal square plus 2 divided by gamma plus 1 m1 normal square. Okay. I can regroup this such that it will become something like a plus b by m1 normal square, okay. It will just become that, I will divide the numerator denominator by m1 normal square, it will just become something like this, okay, where the a will become gamma minus 1 by gamma plus 1 and b will become 2 by gamma plus 1, and you will get to this point. Okay. So, now I want to write it as u2 normal equal to u1 normal into, let us say I want to write this m1 normal in terms of u1 normal, of course it will become a prime plus b prime by u1 normal square. So, this looks like A prime u1 normal plus C by u1 normal, something like this. This is not a simple function in u1 normal, that is what is our problem currently. Okay. Now, if I say my u1 normal increases, why am I saying u1 normal increases? Beta increases. We go back to the previous board where we said that if beta increases, u1 normal increases from here. I am going to use this. Okay. Beta increases, u1 normal increases, and because when u1 normal increases, I can probably say that u2 normal increases if this term is dominant. Okay. If linear term is dominant, okay, or if u1 is high, I will tell it that way. If u1 normal high, if this is very high, then 1 by u1 normal will be very small, then this term will become dominant. Okay, that is easy way to look at it. If not, u2 normal decreases if u1 normal low. If it is low, then this ratio will be very high and this will be very low. Okay. Then it will go the other way. Okay. So, now this is not a simple thing, and this is what is causing all this reversal in theta. Okay. We go back to our theta formula. Actually, I want to show this whole thing, hopefully we will show the whole board, this end up to here. Okay. Now, if I have, we already showed that if I increase beta, the second term will always decrease, that is monotonic, we saw that. If that decreases, theta should increase. Now, I will go and look at the other one. I am going to say if beta increases, if my u1 normal is high, if my u1 normal is high, if u1 normal is high means my beta is high. Okay. If beta is high, then u2 normal increases, V anyway drops. Okay. V always drops, that we have it here. Okay. V drops, u2 normal increases, which means this term decreases. Okay. If this decreases and this decreases, now I do not know where it will go, but based on numbers u2 normal is less than u1 normal, so this is more than this, but the difference is decreasing. Okay. So, I am going to end up with a case where theta will decrease. Okay. So, like that, it is a little more complex, I will not get you any more physical field than this. Okay. This is the closest I can get to. After this it is all math. Okay. You can probably, you have to go and draw the functions out by yourself once and then only figure out the physical intuition from here. It is not very easy to get the full physical field, that is why that is what I told when I started also. Okay. That being said, I want to give you a feel for what happens when I change gamma. Okay. Let us not discuss any more about this, this is the best I can give you there. We will go and change gamma and we will see what happens. Okay. Let us go to the screen first then, it is easier to finish off with the screen, then we will come back to here. Okay. What I have plotted is deflection angle versus beta, same as our theta versus beta curve, and I have drawn it for two different Mach numbers 1.5 and 3. For each Mach number I have drawn it for 3 different gamma values, 1.3 on the top, 1.4 in the middle, 1.67 in the bottom. Okay. Of course, all of them reach at 90 degrees at that corner. Okay. And when I look at each individual plot, it looks like whatever we have been seeing all this time. I just want to see the difference between them currently. Okay. If I go from 1.4 to a higher gamma, that is a less compressible gas, what we are finding is the beta is higher, first observation. If the gas is less compressible, beta increases for weak shock solution. I go to the strong shock solution, it is the opposite. If I become more compressible, beta increases. Previously it was when it became less compressible, beta increased for weak shock. In strong shock, if I become more compressible, that is I go from higher gamma to lower gamma, I am going to increase my beta, it is going opposite, they have different trends. And one more important thing, the theta critical is higher for more compressible gas. 3 different observations we want to explain. Okay, of course, I do not need to explain the weak shock strong shock difference currently in this course, it is not really important. all you need to know is that the curve shifts up by itself as gamma decreases. That is enough for this course. I just want to give a little more in case you want to learn a little more. Okay. And the same trend happens for every Mach number, it is the same thing, I do not need to show it again, but anyway I will just show it once more. For Mach number 3 for weak shock solution, let us say I will pick theta deflection of 20 degrees. What I am seeing here is as I increase gamma my beta increases. If I go to strong shock solution, as I decrease gamma from 1.6 to 1.4 to 1.3 my beta increases. Okay. This is our trend currently. Now, we will try and explain each of these 3 points. Of course, the third point was that theta critical increases. The first one is easy to explain, the weak shock. So, I am picking a particular case and we have theta less than theta max or theta critical, whichever way people call it differently. I am going to have a shock. This is my original beta for one particular gamma value, this is our theta. Now, I am saying the gamma changes to more compressible gas, which is gamma decreases. If I pick gamma decreases, okay, let us call this one less compressible. If it is more compressible, then I am going to have lesser gamma. In one way of thinking about it, my gamma is lower, speed of sound will be lower. If I think about it that way, the wave from here does not go this far into the flow, against the flow, it will go lesser and it will end up with this angle, beta will drop. That is one explanation I can give, beta prime more compressible gas. Okay. Another way of looking at it, the flow incoming is so fast that if the gas is more compressible, it will compress whatever is behind the flow, behind the shock to a smaller volume. Okay. Or if I put streamlines like the way we explained things before, previously the streamlines were like this and the gap between streamlines decreased by this much, that is it is getting compressed by so much fraction. If I draw this particular shock streamlines, the other one does not exist for this shock. I will draw the same width at the beginning. Now, you find that from this gap to this gap it is much smaller, that is it is more compressed, the fluid element is more compressed. If it is coming from between these gap, the same width as this, it is much more compressed here than in this case. Okay. That is it is more compressible, so it is getting compressed, easy way to think about it. Okay. This is very simple to explain. Okay. This is our weak shock solution, I will write it weak here. Strong shock solution is completely counterintuitive, okay. Can be explained only if you understand molecular gas dynamics, what the molecule does with the energy given to it. Okay. We will try to explain without that as much as possible, but I am going to use one statement from there. I have to keep the same theta roughly. Same theta, and now I am going to say it is a strong solution. In a strong solution, we already observed that the kinetic energy of the fluid is converted to pressure energy and temperature energy or enthalpy much higher than in the case of weak oblique shock. Okay. So, we are going to use that statement mainly. I am going to say this is my original less compressible situation, okay, and we already know the answer that it is going to be higher. We are supposed to explain that. Okay. If I just make one statement and you just believe me for sure, that is, if it is a strong shock that is forming, we are interested in making P2 by P1 very high. Compared to the weak shock, it is supposed to be very, very high. That is what we observed last time also anyway. Okay. It is supposed to be very high. To make it very high, that is I have to form pressure energy a lot. Where is the energy coming from? It should be from the fluid. So, it is coming from the bulk kinetic energy, the kinetic energy of the fluid element. Okay. So, there should be a lot more kinetic energy to be processed. If I decrease my beta, my U1 normal decreases, which means I will not have enough kinetic energy incoming across the shock. Okay. So, I have to increase my beta, so that increase beta, which will give me U1 normal increasing, which means I have now lot of kinetic energy that I can process from the shock and produce the high pressure. Okay. This is all dependent on one statement. I said I have to increase P2 by P1 to very high value. Okay. We will not explain that part currently here, we will just believe that that is so. Okay. If I assume that, then things are all fine. So, we will keep it that way and move on. I will go to the next case, which is in the front, the theta max is changing. Okay. So, I will keep parts of this board and continue. Let us say I have a body which has theta greater than theta critical, theta greater than theta max or theta critical. Okay. People call it theta max or theta critical, get used to it. Okay. Now, let us consider a case where it is only slightly greater. This is not usually used in math, but I will just tell this is not a common sign. Okay. I am just saying it is approximately equal, but slightly greater. I will pick such a case. Okay. And I have this particular condition, this is for less compressible gas. Okay. And it has to go through a subsonic solution and then go adjust itself along the wall and get out. That is all we did already in today's class. If the gas is more compressible, what should happen? This gap can now be decreased. Why? Similar to weak shock answer, the flow incoming can push the wave more back and keep the gas behind more compressed, because it is more compressible. It is possible to compress, let us compress it. Okay. That is what it does. So, when that happens, flow can get attached. I am just giving you a possibility, I cannot give you exact answer because nobody has proven it exactly this way. Okay. I will just give you that there is a possibility of this getting compressed to a point where it gets attached. And once it gets attached, there is a proof that the weak shock solution is stable. So, the solution will automatically go to from this curved shock to a straight line shock, it will automatically go there, we do not need to worry about that part. Okay. That proof came up only like 2 years back, it is very recent in research, we are still fresh in solving this kind of problems. Okay. So, it goes to this situation. So, I am just using this one statement, if the gas is more compressible, the shock will want to compress it more. I have been telling the statement from normal shock time onwards. Okay. You just keep on telling the statement again and again, so that it is in your brain. So, overall what is happening, it is now attached shock. For this to get detached now, I have to increase my angle much higher, so that it will go and sit outside. Right. This is not the critical angle for this particular Mach number, if the gas is more compressible. That is what we are seeing here. Now, we will go back to that and we will just probably we will have to stop it with this. I will draw it like this. I will not worry about where the peak is shifting, actually the peak will shift slightly to the right, we will ignore that. Okay. Currently we want, I do not know the explanation for that, we will ignore that. Okay. All I can say is we explained that weak shock, this is less compressible, this is more compressible. Of course, you have to draw it again probably on your notes, but I am just giving it to you like this. Less compressible, more compressible. When I go to higher gamma, it is less compressible, lower gamma is more compressible. I am having some curve like this. Okay, of course, I am going to give whatever I am putting on the screen on the website, so that people who are watching YouTube can avail it later. They can print it out and keep it for themselves anyway. Okay. If it is a weak shock solution, we find that beta decreases, we proved it. Okay. If it is a strong shock solution, we proved that as I become more compressible, it goes that way, beta increases. Okay. And you notice that there is no change at 0 deflection, okay. There is no change at 0 deflection. Of course, if it is mu, there is no shock, it is a 0 strength shock, okay. So it just goes through straight, there need not be any deflection. Normal shock again is just perpendicular change, and there is no difference in beta really, there cannot be any difference, beta is 90 degrees, normal is normal. Of course, there will be a difference in P2 by P1 values, slightly, we won't worry about it. You know that P2 by P1 formula has gamma in it, so if I change gamma, gamma will have an effect on P2 by P1. Let us not worry about that part also. The main thing I want to show in this plot is theta critical has now substantially increased, okay. It is not very small number, if I increase my Mach number, this change will be really drastic, okay. You are going to see a huge change up here. Of course, when I go to very high Mach numbers like more than 10 or 15, this change may not be very high, it may saturate to some particular value, okay. That is hypersonic limits, everything goes to crazy there. So I am going to have something like this here, okay. If I had a case where my theta was this, if my gamma was higher, it will have a detached shock, if the gamma is lower, I will have an attached shock. This is related to compressibility, okay. So do we have a solution for solving flow behind a normal bow shock yet? Not really, okay. We cannot solve it for a bow shock, we will just leave it like this. We still have a little bit of stuff left in oblique shocks, we will not deal with it today, we will wait for next class, okay. That will be how will I solve problems, that is one aspect. Other aspect is what if this shock meets something else. These are the two aspects we have to talk about, we will talk about it next class, okay. See you people next class.